Okay, so let's look at our second example. Once again, this is found in your notes. So the first thing we have to do is find the interval of convergence for the original expression. And to find the interval of convergence, we're going to use the ratio test. So we take the limit as n approaches infinity. And once again, because we take the absolute value, we can ignore that alternating part. So this would be x minus 2 to the n plus 1 over n plus 1 times n over x minus 2 to the nth power. And we're taking the limit as n approaches infinity. As n goes towards infinity, we see that this will cancel and we'll be left with x minus 2 here. And this will cancel with this. So we have the limit as n approaches infinity of x minus 2, and that has to be less than 1. Now, because there are no n's in our problem, the limit as n approaches infinity is just going to be this expression, x minus 2. So then we have negative 1 is less than x minus 2 is less than 1. Adding 2 to each side, we get 1 is less than x is less than 3. So once again, this is our interval of convergence, but we need to check excuse me, our endpoints. So to check our endpoints, we put 1 into the original. So I'm checking the endpoint at 1. So I have negative 1 to the n plus 1. I put in 1 for x, so I get 1 minus 2 is negative 1 to the nth over n. So again, this does this weird alternating thing we have to be careful of. So I don't think this is going to alternate because I end up with negative 1 to the nth times negative 1 to the nth times negative 1 to the first power over n. Once again, negative 1 to the nth times negative 1 to the nth is just 1 to the nth. This is no longer alternating, so 1 over n diverges, so this diverges. And then I'm going to check my endpoint at 3. Once again, I'm going to replace x with 3. So I have negative 1 to the n plus 1. So 3 minus 2 is 1 to the nth power over n. Now, because this is a positive 1 to the nth, it doesn't matter, and this continues to alternate. And because it's alternating, it converges. It's alternating, and the limit as n approaches infinity is 0. So this converges. So my interval of convergence is 1 to 3, 3 included, 1 is not included. Okay? So now let's find the derivative. Once again, when we're looking for the derivative, we treat all of this as if it's a constant. So all of that just comes out, negative 1 to the n plus 1 over n. And I differentiate this part. So to differentiate this part, I bring down the n, I multiply by the exponent, and then I subtract 1 from the exponent. Now, you can probably see here that the n's will cancel. So I have negative 1 to the n plus 1 times x minus 2 to the n minus 1. And I am trying to determine, remember my interval of convergence remain the same, so I just have to see, will it converge on the endpoints? So if I substitute in 1 for n, I get negative n to the n plus 1. 1 minus 2, I get negative 1 to the n minus 1. Now, this is just going to be a series of 1s or negative 1s, and whether or not it's alternating is irrelevant. I don't think that it will, but it's irrelevant because I'm just multiplying by 1, so this will diverge. And now we try 3. And sort of looking at it, I can sort of see that 3 is going to diverge as well, but if you want to check 3, so here we checked 1, and here we're checking 3. So checking 3, I get -1 to the n plus 1, and 3 minus 2 to the n minus 1. Once again, this is just going to be 1. So regardless to whether or not this alternates or not is irrelevant, because we know that that limit is not 0, so this diverges as well. And so for the derivative, the interval of conversion is 1, 3, neither are included. Let's do our last example, which is going to be the integral. So once again, when I do the integral, all of this acts like a constant, so I can write this as -1 to the n plus 1 over n, the integral of x minus 2 to the nth power. And recall from the power rule, this becomes, all this stays here, -1 to the n plus 1 over n, and this becomes x minus 2 to the n plus 1 over n plus 1. Okay, so now this is our integral. We need to check our endpoint. So we start by checking 1. We get -1 over n, yes, that's to the n plus 1, sorry. And putting in 1 into this, I now get -1 to the n plus 1 over n plus 1. Now, once again, notice this is going to give me n squared plus n. I know, or you should know at this point, that no matter what, regardless to whether or not this is alternating or not, that's going to converge. When I check at 3, I'm going to get something very similar. I'm sorry, that should be 3 minus 2, which is 1. So that looks very similar, and it doesn't matter if it's alternating or not, because n squared plus n will converge no matter what. So my interval of convergence for the integral would be 1 and 3 both included. Okay? So here's the big ideas from this. You integrate, when you integrate and differentiate, you only do it to the x part of the expression. Everything else acts like a constant. And then to check the interval of convergence, you only need to check the endpoints. Because the interval of convergence will remain the same, it's just the endpoints that could change. So that is it for the second video. We'll do homework tomorrow in class, and have a great day.